The test is April 18th. So it's going to be really, really fast. We have one activity or lab. Okay, so you got 10 days on this. That's it. So hopefully you did what I asked you to do and finished your Learn Smarts and finished most of your homework. If you didn't, you're going to have to kick it in gear and get it done fast. Okay? The stuff that we do today won't make a lot of sense unless you've done some Learn Smarts. So here we go. We're going to get started. Organic chemistry. This is one of my favorite. It is the chemistry of life. Okay, so it has to do with just carbon and hydrogens. Okay, for the most part. There are other things we'll add in later, but carbon and hydrogen are the big thing that make it organic. Organic is everything that has been living at one time or another. Okay? So, organic chemistry is the study of compounds that contain carbon. Now, this does not include carbonates. It does not include acetates. So, if it's in an anion, okay, then the carbon is not a carbon compound considered. Okay? The carbon has to be the main body of it. Organic compounds are in virtually everything. Everything, living everything. Okay? We use products in food and clothing and medicine and gasoline and refrigerants and soap and everything. We can use natural sources like cotton, wool, or silk, or we can use synthetically produced. So a lot of the stuff for exercise wear now is synthetically produced. Stuff that is odor controlling for exercise wear usually has silver in it at some point. They've meshed silver in. So we synthetically produce things. Some examples of some compounds here. Methane is the simplest organic compound. It has 1 carbon and 4 hydrogens. It is what we use in natural gas. It's what we're using in the lab for our gas. It is what you use in your house for your furnace. Ethanol is one of the small alcohols. It is the one that is in alcoholic beverages. Now, when they had prohibition and they tried to make alcohol on their own, a lot of people would try and get alcohol out of wood, and they called it wood alcohol. Wood alcohol is actually methanol. And methanol, when used in our bodies, turns right to formaldehyde. So they would call it white lightning, because the first thing that formaldehyde attacks is the optic nerve. And so they'd see a bright flash of light and then they'd croak. And it was a very painful death. So going forward here, capsaicin is another one that is a big molecule for organic. You can see how huge that is. That is what is in peppers. It's responsible for the spiciness, so like in your jalapenos and your habaneros. It probably won't be listed as capsaicin, but it's also used in topical pain relievers. So they use that as topical pain relievers. Okay. Caffeine. Some of us get it from chocolate, others get it from coffee or colas. This is also an organic. You can see that we're worried about, in organic chemistry, the structure. It's a lot about structure. And we're going to be working with a lot of structure. Okay? All organic compounds contain carbon, like I told you. They contain hydrogen. Carbon always has 4 bonds. Hydrogen can only have 1. Okay? Methane shown as a Lewis dot or simplified into the line diagram. Okay. Carbon forms single, double, and triple bonds, sharing either 2, 4, or 6 electrons, and it does affect the shape. So this is where I want you to start playing with your molecules. So we need 2 carbons. Carbon's black. You're going to hook 2 black carbons together with the stiff bond, okay? And then you're going to get 6 carbons, or 6 hydrogens, and attach them with stiff bonds to the carbons. Okay, this is a 3D molecule. This is ethane. Ethane can spin in space like this. Okay, it can spin around that bond like that, but that's about all it can do. It can wiggle a little bit side to side, but not a lot. But it can spin in space. And the reason it can't wiggle side to side is because these hydrogens become too close to each other and they repel. Okay, so it can spin in space like this. So everybody got this built? We're going to be building a lot. So now, you won't be able to use these on the test, but you've got to be able to visualize in your mind what you could make as a 3D molecule. Okay, so this first one is ethane. Does it look like what you drew, like you draw on the flat? It doesn't really. Okay, so you've got to sort of see what the 3D is coming forward. Now, what I want you to do is I want you to take two hydrogens off. I want you to change the bond in between from a stiff single bond to the two bendy bonds. So the bendy bonds look like this. They bend. Okay. We're now going from ethane to ethene. So we're going to put the bendy bonds in like this. Tell me what happened to the molecule when we took off the two and made a double bond. Okay, so this is, yep. I sort of relate this to my four appendages of my body, right? A single bond would be like a handshake. A double bond would be like holding two hands. What happened here? Can it spin? Can it move at all? Up and down, right. Tell me what it, so we had before it was a 3D molecule. What dimension is this? It's a 2D. So it is all in a plane. Right? It sits in a plane. Okay, now we're going to take two more hydrogens off and just keep them attached to the white because we'll be using them later. Grab another bendy bond, and connect this. So we're now making ethwyne, or ethyne. Yeah, I call it ethwyne. It's, they call it acetylene is another common name for it. Okay, tell me what happened here. Yeah, you're holding two hands and you brought up your knee, right? Okay, so this right here is a triple bond. Tell me, how does it move? It doesn't. It's very, very rigid. What is acetylene? Does anybody know what acetylene is used for? It's used for welding, for very high temperature welding. Triple bonds have a lot of energy in them because they are very rigid. When they try to break them, they give off a lot of energy. So this is now, we've gone from 3D to 2D. What's this? It is a line. It's 1D. Okay, one direction. Okay, all right, we're going to leave that alone for a minute. We're going to come back to it in just a second. We're going to do some more notes. So single and double triple bonds. So remember, handshake, single bond. And we could move around that. That could twirl around, right? Double bonds, like holding two hands right forward. We could go up and down, but that was it, right? This is my triple bond. I couldn't find somebody doing that. This is my very expert drawing. Ha ha. Okay, triple bond. You have one leg to stand on, and that's it. And it's sort of wobbly as far as it will have a lot of energy. It wants to break. It doesn't want to stay there very long. We do not have a quad bond. There is no such thing. You got to have at least a leg to stand on. Okay, you can't use your bums. Okay, so none of that. All right, so we have chains of atoms. Some have rings. Now, tell me, what are the angle on an equilateral triangle? What are the inside angles? If I have a triangle, how much do they all add up to? Let's do that. 180. So if they're all equal angles inside, 60. If I have tetrahedral, pretend like these are white. If I have a tetrahedral, what is the angle between here and here? Nope. 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 Is that 120? This is 109.5. Okay, this is the angle that carbon wants to have everything come off at. It's 109.5. What happens when I put it in a triangle? It becomes 60. That's sort of like putting it into a triple bond. It's really stressed. But that is the smallest cyclic that we have, is cyclopropane. So cyclic propane, propane. Propane is much more stable than cyclopropane. Okay? This is 109.5, just regular, and this one is 60, right? So you can see it's really stressed. The more angle we squish the stress, the more stressed it gets. Okay, go looking at this one. Organic compounds also contain other elements besides carbon and hydrogen. If they contain other elements, they're called heteroatom. If they're heteroatom, we look at what's going on with the bond. So if it's just carbon and hydrogen, it is nonpolar, it is organic, there's nothing we worry about. But if we add something like nitrogen, oxygen, sulfur, I forgot to put sulfur in there, chlorine, bromine, or iodine, then we have to worry about what other things are going on. We still worry about the outer octet. Every element wants an outer octet except for hydrogen, which only has 2 in the outer shell. Okay, but carbon must always have 8 around it. Okay, and all the rest must have 8 around it. We can't just throw one in there without that. Okay, so looking at these, and we would put sulfur under here too. Sulfur would also be here. Sulfur bonds like an oxygen. So hydrogen 1 bond, carbon 4 bonds, nitrogen 3 bonds. Oxygen and sulfur, 2 bonds. And halogens, fluorine, chlorine, bromine, iodine, 1 bond. It also tells down here at the bottom the number of non-bonded electrons, and it goes up opposite of the number of bonds it will make. Okay? Everybody got that? Not quite. Okay? Are you two awake? Okay. Getting it down? All right, so we're going to play with these a little bit more. So, if we have an oxygen, so we're going to take one of the carbons, and we're going to take and put 3 hydrogens on it, and we're going to put an oxygen. Oxygen is red, and you'll notice oxygen has 2 bonds, so we're going to have to grab one of our hydrogens and put it on there. This is methanol. This is wood alcohol. Okay? Methanol has a funny shape. It looks like a R2-D2 or something. I don't know what, looks like you've got a robot that's scanning or something, because this can go around. Okay? This is an alcohol. Now, in our body, what happens is 2 of the hydrogens come off and make H2, and when they do, we grab some bendy bonds, and we attach the oxygen with bendy bonds instead of a solid bond, and we get formaldehyde, or methanal is the IUPAC name. This is methanal. This is what will kill you. Okay, our body processes methanol to make methanal or formaldehyde, and this is what kills you.
Oh, wait, this is formaldehyde.
Yep. Now, if you drink alcohol, what happens when you drink alcohol is you end up with ethanol in your body. And ethanol looks like this. This is what gives you the hangover. If you drink too much ethyl alcohol, then this can also kill you.
Is that like alcohol poisoning?
Yep, also known as alcohol poisoning. Okay? All right, so we're going to come back to that. We're going to be using Vesper theory. Vesper theory basically says that the central atoms, the most stable arrangement keeps the groups on the central atom as far away from each other as possible. In an atom surrounded by 2 groups, is linear and has a bond of 180. So when we went back to our ethene, right? Or acetylene, ethine, sorry. The triple bond forces the hydrogen exactly opposite those bonds because it wants to be as far away as possible. So we get 180, and that gives us our lyene. Yep. Be good? Okay, when we had our double bond, I'll take this one bond off. When we had our double bond, we ended up in a plane, right? And when we ended up in a plane, the angle between the bonds, between this bond and this bond and this bond and this bond and this bond, we know that in a circle there's 360. Well, there's 3 bonds. It's going to cut it evenly, 120. Okay? Now, if we look at our original methane, we have an angle of 109.5, and we need to remember that angle, 109.5. We learned earlier that in when we had one ghost or one unshared pair of electrons, it scared it down by 2 to 107. When we had 2 unshared pairs of electrons, it scared it down by another 2, 105. In this next 2, possibly 3 tests, I've got to look at the last one. She just uploaded it. She will refer to it as about 109.5 for all of it. Okay, so this is 109.5, and then if I have 1 unshared pair of electrons, it will be about 109.5. If I have 2 unshared pair of electrons, it's still about 109.5. So she doesn't distinguish between 107 and 105. Okay, she just says about in front, or approximately. Okay, all right, so going forward, remember that's a tetrahedral shape. When we draw it, we need to be able to show this in drawing. So to do a drawing, we use the dash, dash, dash to show it's going behind, and a wedge to show it's coming out of the plane. So we take and put some of them in the plane. That would just be the regular lines. And then what's coming out we would show as the wedge. What's going back we would show as dashed. Okay, so you need to be able to do that and be able to see what's going on. Instead of just showing this molecule like this on a flat piece of paper, you need to understand that some of it's coming out at you and some of it's going back. Because when we understand that it's a 3-dimensional molecule, we can see if it's become polar or not polar, and we'll talk about that in just a minute. So, tetrahedral shape. She'll be asking you what shape element is in a big molecule, so you have to be able to look at that. When we look at nitrogen, nitrogen is your blue, so grab a blue. This right here represents an unshared pair of electrons. So if you've got one of those, you might not be gray, you might be purple, you might be pink, you might be some other color, or you might have to borrow ones from your neighbor. You're going to put that at the top. Then you're going to put your 3 white at the bottom. This is an ammonia molecule. You can see that leaving the white on the peg makes life a lot easier when you're making molecules because you're forever using whites. Okay? If we take and we attach this to a methane molecule, we're going to take off 2 hydrogens. And we're going to get another bond and just attach it. This is what we have on the screen right now, is this molecule right here. One from each, one from the methane and one from the... Okay, so we get this molecule right here.
Is it a hard bond?
Yep, hard bond. The only time you use the bendy bonds is if you have a double or triple bond. Okay? All right, so basically, they saying right here is 112 degrees. Remember I told you that these would be scared down a little bit? Same thing happens, but she will just say it's about 109.5. Okay? All right, next one. This is methylamine, by the way. A mean little critter. The next one is oxygen. And when we have oxygen attached, I'm going to take this one, put the oxygen back on. I know it shows. I'm going to do it with 2 carbons just because I have the 2 carbons already attached. You can do it with 1. So this is ethanol. This is my little dog, I like to call him. There's legs like that. So cute, right? Okay, they've got methanol up there. This is ethanol. Again, the unshared pair of electrons right here are not, we don't put the little ghost in. We only do the ghost for the nitrogen. The oxygen's already just set. Okay? So 2 lone pairs. So this is a table that I gave you that's on there. Now, there should be one set maybe that is out there that has just 3 holes around it. It's got I think it's brown or light tan. Look in your thing and see if you've got it. It just has 3 holes around it. Not everybody got that because that set is more expensive. So look real quick at your sets. Does anybody have one with 3? With 3. It's like a light tan or brown, but it will have only 3. Only 3. Does anybody have that? Okay, so we're just going to have to pretend. The trigonal planar, it will sit right in a plane. Okay, it will be a triangle in a plane, and that's it. Okay, the tetrahedral is what we've been doing with our carbon. Trigonal planar is what we will see with our nitrogen, and then the bent is what we're seeing with our oxygen. Okay, so there's several different shapes that can be in one molecule. Now, we need to learn how to do condensed structure. So when we have this is a regular structure. Okay, when we condense it, this is what they usually use in textbooks when they condense it, because it's a lot cheaper for them to write it like it is on the right than it is to have somebody draw it and then take a picture of it and then put it into the program. So this is how they would do it. This represents a CH3. This is a CH2. You can see that there are 2 CH2s, right? There's a shorter way to do that, and I'll show you on the next slide. But basically, for me, I have to draw it out like this on the left before I make a condensed structure. I cannot just look at something or read the name of it and then do the structure. It's too hard. Okay, so let's look at the next one. On this one, we have some more things going on. We have another methyl group that's attached to this group. So sometimes they keep a vertical line here. Sometimes they don't, because that vertical line is, again, more money for textbooks. So they sometimes write it like this: CH3, CH, parentheses, CH3, CH2, CH3. So that's how they would write it more often than not. Now you'll notice on that second carbon I wrote the CH first and then put in parentheses CH3. You always put your most electronegative last when you're listing stuff. Okay? Unless it's oxygen with a hydrogen, then it's OOH or OH. We okay to go forward? Okay, so this is what I was telling you earlier. If you have 2 groups that are exactly the same in a condensed structure, you can actually simplify and put it like this. So if I have 10 CH2s, I don't have to write 10 CH2s. I can put it in parentheses and put a 10, which is nice. I can do it really quickly. Again, I showed you this already, but this is another way. This carbon right here has 2 CH2s attached to it. Because it has 2 CH2s attached to it, they can put that first and then put that, or they can write it like this: CH, CH3, 2 CH2, CH3. The reason why they did it this way is to show that they were on the outside. But either way would work, okay, for condensing it. Any questions with condensing? That's really weird. Just take it a little bit at a time. Okay, I want you to try and condense these 2 on your own. I know they're not in your paper. Just find a place where you can write down what you think they would be.
So we just write like this.
I want you to do the CH3 blah, blah, blah. Yep. I'm going to give you about a minute.
You go left and right or like?
You always start on the left and go to the right. Yep. Just like you're reading. Hi.
Hi. Caleb Brown and Tyson Denny.
To do what?
Huh? It's for you. We have to ask them questions.
Okay, make it quick. Okay, got about another half a minute. See what you can get done. You will need to go back and forth between this structure and the condensed structure on the test. My suggestion is do not look at the answers until you have got your answer. Does that make sense? Because she will try and trick you a little bit. And if you look at her answers before, you'll say, oh yeah, that one's right, and it will be wrong. Okay, so on the first one, you need to be careful because this carbon right here has these two coming off of it, right? So we want to put those two together. Two ways. Remember that they did it like this, CH3, parentheses 2, CH, like that. Or you could do CH, parentheses CH3, 2. And then go forward. So then we go CH2. And then again on this one right here, we've got two carbons coming off, or two CH3s coming off. So we're going to go, I'm going to go CH, parentheses CH3, parentheses 2, CH, parentheses CH3, parentheses 2. I like the consistency of this one on the bottom. That's the way that I was taught. She flips back and forth. So know both ways.
I got that right.
Okay? The next one over here, we're going to go and we're going to say, oh, the first one I have a CH3. The next one I have a CH2. Then I have a CH2 with an oxygen. Right? It's not a CH2, but it's a CH2 with an oxygen. So I'm going to go CH2O, and then I'll go CH2Cl. Most electronegative last. Now, she could have done this. She could have done CH3, CH2, 2O, CH2Cl. That's still okay. It's not great, but it's still okay. This one is preferred over the bottom one, but she can do either way. Okay, so next page. This is what she could have done. So she could have taken this and made this look like this, where she shows you where they're coming off, or put it completely into condensed. Does that make sense? Okay? Same thing here. If I have two groups that are the same, I can further simplify it by putting them together. Okay? All right, so when you're drawing a skeletal structure is line structure. They're basically the same thing. So when you hear skeletal, think line. Stay with me. Don't fall asleep. He's going. Boink. Okay, stay with me. Okay, assume there is a carbon atom at any junction of two lines. So if I'm going like this, this would represent a carbon to a carbon to a carbon. Okay? So any joint or at the beginning of any line is a carbon. Okay? Assume there are enough hydrogens to go around. In a skeletal drawing, you don't draw the hydrogens. You just assume they come around. Okay? Each carbon needs 4 bonds. So I would assume that there are 3 hydrogens coming off here, 2 hydrogens coming off here, and 3 hydrogens coming off here. But I haven't drawn any of them in that. Right? Okay, so you're going to draw in all the heteroatoms. So if there's a nitrogen, if there's an oxygen, if there's a sulfur, if there's a fluorine, chlorine, bromine, iodine, I draw them in. if they have a hydrogen directly connected to them, I show it. So for instance, here is this. If I had a nitrogen right here and it had 2 more hydrogens, I would draw that in. Okay? All right, so let's go forward. This is an example of a cyclic in line diagram. This is full out, full structure, but I draw it like this in a line diagram. So I'm basically doing geometry, right? If you've ever gone to the pharmacist and you got the little paper that comes out, you can actually see stuff like the hexagon and some pentagons and other things, weird things next to them. Okay, if there is an OH group, you show the OH group. Okay? Carbon and hydrogens just go away. They're just part of the line diagram. Okay? When you have a functional group, this is what tells me what's going on. Now, if you go on to 1120 and finish the series, which I highly suggest you do at the college, so that you have a series of physical chemistry and you're done with your physical chemistry at the college, or physical science at the college for your generals. You will go into each of these groups that we're learning about in this little thing for the first 6 chapters. So you'll learn about nitrogen attached, which is amides and amides. You'll learn about oxygens attached as double bonds in aldehydes and ketones, and as in carboxylic acids, as alcohols. You'll learn about esters and ethers. You'll learn about different structures, but each chapter is on one type. Okay? This is known as a functional group. The carbon backbone is the longest carbon chain. Okay, and we often represent that as R. We okay to go forward? Okay, so hydrocarbons, basic ones, alkanes, single bound, all the way through. Alkanes, single bound. Alkenes, double bonds. Alkynes, and I say it whiny on purpose, it's actually alkynes, but alkynes, triple bonds. And they're whiny because they have to share 3 bonds with one person. How can anybody be expected to share 3 things with one person, right? Okay. Aromatics have a benzene ring. What is a benzene ring? A benzene ring is a 6-member carbon that would be drawn like this, but every other bond is a double bond. Now, that can go back and forward between this, where the double bonds are here, here, and here. So we just draw it like this and put a circle in the center. The circle in the center says every other bond is a double bond, because who knows where those double bonds are at any one time. They can flip and flop all over the place. And if you actually look at a benzene ring, it actually is a 1.5 bond at each place, because they're flipping and flopping back and forth between these first 2. So it looks like a 1.5 bond. Okay, so I've gone through and I've given you some charts here. What is an alkane? What is an alkene? What is an alkyne? What is an aromatic? Okay, and then it goes down farther. What is an alkyl halide? Halide means it has a halogen. What is an alcohol? It always has an OL. What is an ether? An oxygen in the middle of 2 chains. What is an amine? Amine has a nitrogen at the end somewhere, or in the middle of a chain, but nothing else with it. A thiol has sulfur, and these are the stinky ones. Thiols are what skunks give off. Okay, these are thiols. So an ether, oxygen in the center. Okay, ether this or that. That's how I remember it. Ether this or that. Okay, oxygen's in the center. It can be part of a bigger compound. Here we have an ether, but we also have an alcohol. So on the more complex molecules, they have more than one functional group. Okay? Carbonyl groups, this is also in your assignments. Carbonyl groups can be at the end, where on this side there's a hydrogen, and that would be an aldehyde carbonyl group. We can also have it in the middle of a carbon chain, where this is an R and this is R prime. That would be a ketone, okay, carbonyl group. We can also have an OH on this side with an R on this side. That would be an acid carbonyl group. So carbonyl groups can be part of many different compounds. Okay? But a carbonyl group is just a double bound oxygen. Here are some of them. Like I said, the aldehyde, where you have the H on the end. Ketone, we have two different R's. Carboxylic acid, OH. Ester, we didn't talk about ester, but ester has an OR, so it has an O and a chain going on. An amide has a carbonyl, but it also has a nitrogen that can go on to a chain or a hydrogen. Now remember, we're just touching these. You just need to be able to identify them. When you get on to 1120, they actually go into naming each one of these kind of things. And once you learn how to name one, it's really easy to learn the others. Okay? All right, so functional groups, the double bond oxygen, the carbonyl. The aldehyde is just got a hydrogen right here. It is ending in a condensed form as CHO. Okay, CHO. For an acid, they often do COOH or CO2H. I've seen this way more often than the other way. Okay, that represents an acid. And acids, remember how we named acids in inorganic chemistry? It was ic and acid. Well, in organic chemistry, we go oic acid. And that's because they're really gross. But they're also organic, so that's where the O comes from. Okay, so oic acids. Ethyl acetate, this is an ester, and esters are smells. And we're going to do a lab on Friday where we get to make smells. So, and it's not really a lab, it's an activity because you don't get credit for it, but it will help you to understand what's going on. You can choose what smells you make. Now, we won't have stabilizer. We'll take an acid, we'll take an alcohol, we'll mix them together, warm water and a catalyst, and we'll get to make smells. And you get to choose, do I want to make mint or pineapple or banana or whatever flavor smells. Okay? But you don't want to take them out of lab because they don't have a stabilizer and they will separate back into their acid and their alcohol. And like banana is made with butyric acid, and butyric acid smells like vomit. And if you get it on you, you smell like vomit for a month. So you have to be really careful when you're working with them. Okay? So here are some of the smells that we could possibly make. Cherries or almonds, benzylaldehyde. Benzyl alcohol, I don't know if I've got any more of that left. Isoamyl, amyl just means 6. So amyl, another name for that would be hexanol. Okay? Isoamyl means just isohexanol. That's banana. Citric acid, we've got some things going on there that has 3 acid endings. And then here's the butanate, the odor of pineapple. Okay, so organic bonds are covalent bonds, sharing bonds. Okay, organic compounds exist with much weaker forces than inorganic or ionic compounds. They have lower boiling points and melting points, and usually are a gas or liquid at room temperature. So if you think about it, methane gas we use in lab is a gas. Propane is a gas. Butane is a gas. Once I get to pentane, it starts to get to a liquid, but it quickly goes to a gas if it gets very warm. Then we get to octane. Octane is what we put in our cars and trucks as gas. It's a liquid, but in hot weather it will vaporize very quickly. But then we get up to waxes. Waxes have like 42 carbons long, and that's when it finally gets solid. Okay to go forward? So you'll notice we're not doing much math, right? There's no math in this one. It's all just looking. All right, now remember I told you that it's basically nonpolar, except when we get these heteroatoms in there. And when we get those heteroatoms in there, we have to look and say, okay, oxygen, the ones that we're adding are close to being, the electronegativity is high. So they'll pull a slight negative to a slight positive. So overall, I get what's known as a dipole, where it has a slight negative side and a slight positive side. In small molecules, in small organic molecules, that makes a difference. In small organic molecules that have a dipole, they will dissolve in water. Large molecules that have a dipole will not. Okay? Regular organic molecules will not. Oil and water don't mix. We know that. But isopropyl alcohol and water do mix. So the negative positive is a big deal. We okay to go forward? Okay, so looking at hydrocarbons containing just carbons and hydrogens, they're nonpolar. They won't dissolve in water. They will only dissolve in carbon compounds. If we have a small molecule and we can see that there's a negative side and a positive side, it will dissolve in water. If they're very big, they won't. Now, chloroethane, we had trichloroethane, or TCE, that was coming off the base that got into our water supply. And the bad thing is it dissolves in water, and it causes cancers of all kinds. And they were having a hard time getting out of the water. They tried bubble veil. They tried a lot of different things. They couldn't get it out. Okay? It was coming off Sunset area, into the Sunset area. It also went down over the hill into the South Weber. Yeah. Okay, so if we have dipoles, we've got to look at each dipole. If they act against each other, then the molecule is not polar. If they don't, then the molecule is polar. So here we have dichloroacetylene or ethylene. You'll see these arrows. These arrows have a positive on one side. It's always pointing to the negative. Okay? So because these arrows work against each other, where I have positive in the center and negative on the outside, that molecule is nonpolar. But if I have molecules like this one, I have positive here and it's heading to a negative, positive here, it's heading to negative. I have a point at which I can separate the positive and negative. I have a dipole. Now, it's not a full positive and it's not a full negative. It's just a partial. But it's enough to give that molecule a dipole. And dipole just means two poles, right? A positive pole and a negative pole. All right, going forward, you okay? All right, I want you to make this molecule. I want you to draw this molecule before you make it. I want you to tell me if it's polar or nonpolar. So, explain why CH2, Cl2, is a polar or nonpolar molecule. Cl2 is represented in your model kit with green. It only has one hole. I want you to draw the molecule, and then I want you to make the molecule. I'm giving you 2 minutes. Then tell me if it's polar or nonpolar. Polar or nonpolar? Draw it first. Draw it first and then make it. Carbon's black, hydrogen's white, chlorine's green. 2 green, 2 white, 1 black. It's a stiff bond. So we don't know what the others are for? Great.
Or nay were the only ones that worked that kind of stuff.
All of them? And we locked them?
All of them?
Inside the inside lab and the outside lab? The little lab?
I did the one right outside of the room. Do I need to clean the one right there?
So they didn't want the back, wait a minute. They didn't want the back lab?
They didn't want the environmental lab.
Okay, so that's a back lab.
Yeah.
And you clean that one up. Okay, but did you check the keys on the little lab inside
Do you mean with the girl?
with the glass? Uh-huh.
Yeah, we went in there and we checked all those cabinets.
And the
There's
only,
those one keys, those are the only ones, same lock, everything.
well,
But
where
we
are
tried
the
all the
others?
other keys, they didn't work.
Wonder what all the others are
And we
for.
pictured them.
Okay,
Yeah, that's what we were asking, like we learned about before.
Great.
So,
Okay.
CL or CL2?
Green is Cl. So you have 2 Cls. Got 30 more seconds. Make a decision. Is it polar or is it nonpolar? Okay, I want you to also draw it 3-dimensional. So you drew it just normal, but I also want you to draw it 3-dimensional with the hashtag and the wedge.
Is this right?
Dashes.
So a dotted line.
15 more seconds, and we're going.
Say a dotted line.
It's sort of like a hashtag lines going through. Well, not hashtag. That it's like that kind going back, or the wedge coming forward. Okay, thumbs up if you think it is nonpolar. Thumbs down if you think it's polar. I only see 2 thumbs, 3 thumbs, 4 thumbs. Come on, commit. Commit, commit. Polar or nonpolar? No. Polar or nonpolar? It's polar. Good. It is polar. Good. Okay. The reason it is polar, if you just went and drew this on the paper, if you just drew this on the paper, this is what you would draw, right? Okay? That's what you should have drawn. But you should know that this is a tetrahedral. So when I draw it, I should be drawing it like this with the lines showing me one's coming out, one's going in. When I do that, then I can say, oh, that's going back in the paper. This is on the paper. I can cut a line right here and separate my chlorines. Now, if you happen to draw it like this on your paper, would it look like it's polar? It wouldn't, but what if I did this? Then you can see that it's polar because those 2 go back in and the other 2 come back out. Yes?
So when you drew it in the 3-dimensional one, does it matter if you have a CL and the H on the straight line?
Nope. Nope, you could put it any which way because, right, I can twist it. But if I look at it, if I think in my mind, this is what you need to do, because you won't be able to have these on the test. You need to be able to visualize what it would look like. Okay, so if I can visualize, oh, my chlorines are here and my hydrogens are here, I can cut that. I can get the chlorines on one side and the hydrogens on the other side. So I'm going to have a polar molecule. Does that make sense? Okay, so let's go forward. All right. Rule of solubility works. Like dissolve like. So organic dissolves organic. Most organics are soluble in organic molecules. They usually say carbon tetrachloride. We found that carbon tetrachloride is very hazardous to most people's health, so we don't use that. Most organic compounds are soluble. I was telling you earlier, if you have a small organic molecule that has a polar, like ethanol, we can make it a pole. It will be soluble in water. That's why when we have drinking alcohol, it's mostly water and a little bit of alcohol, because if we drank pure ethanol, we'd die. Okay? Polar organic compounds are soluble, like I said, but they only have to, this is the big key. They'll only be soluble if they have an oxygen or a nitrogen. Sulfur doesn't work. It's too far down. It doesn't give enough of a pole. Okay? And the rest are the halides, and halides can only be bound to one thing. Why would they choose nitrogen and oxygen? Why would only those be soluble in water? Think about our bonds. We talked about dipole before. We talked about hydrogen bonds and LDFs. What were hydrogen bonds? What did it have to be hydrogen bonds? You've got to remember this for the end of the year test, so you might as well review it now. Hydrogen bonds have to have a nitrogen, oxygen, or fluorine directly connected to a hydrogen. Well, if fluorine is directly connected to hydrogen, it only can have one bond, so it can't be connected to a carbon. So that one's out. That leaves nitrogen and oxygen. Both of those need at least 2 bonds. One oxygen needs 2, nitrogen needs 3. So it can be directly connected to a hydrogen and to a carbon compound. Okay, so we can do hydrogen bonds. Okay, so looking at a molecule. Hexane, nonpolar, just carbon and hydrogen. Ethanol, right here, is polar because of that oxygen, hydrogen bond. Okay, so it can hydrogen bond. So that makes it soluble in water. If we look at very large molecules like cholesterol here, cholesterol has an OH bond, but it has a big rest of the molecule. And that big rest of the molecule is not going to be told what to do by that little teeny polar bond. And so it is nonpolar. Okay, it's insoluble in water. And that's where we're going to stop there for today. So